Greetings and welcome, friends. Mr. Wadi here. We're in page 204, Big Ideas Geometry textbook. We've been talking about like transformations and compositions of them and congruence between the image and the pre-image. Good stuff, good stuff. It says exercise 3, identify any congruent figures in the coordinate plane. Explain. All right, someone spot some congruence here. What do we got? I see like this little right triangle sliver guy, right there. I'm thinking that guy is congruent to this guy right there. So I'm going to call that triangle JHK is congruent to triangle. And now the order in which I name this is specific. What triangle name would correspond with the letters that I have chosen? RQS, yeah, it goes from R to the right angle to the S. RQS. Why, using the language of transformations, do I suspect that that maps onto that in a congruent fashion? What type of transformation would take me from here to there? One of the many. Specifically, though, a rotation of, looks like, negative 90 degrees, or I'll just say 90 degrees clockwise. About what point? About the origin, I'm guessing. All right, yeah, let's look at K. Let's see, can I draw this? To S, that should be a 90-degree angle about the origin, and the same, I believe, would happen for the rest of those. Did someone find maybe there's a composition of transformations so that perhaps there's like a double reflection, but I think anything like that's just going to get way more complicated. Let's try the classic rectangles here. Let's see, these are 3x1 rectangles. I'm guessing that rectangle MNLP is congruent to rectangle what now? Theoretically, there's multiple ways I could name this, but EFGD looks like it's a translation. According to the transformation rule, what happened to the X here? It looks like so L went over 1, 2, 3, 4, 5, 6, 7 spaces, so X plus 7. And Y minus what number? L went down 1, 2, 3 to become the new D, so Y minus 3. Is there another transformation that you could easily do? I was seeing a rotation. Yeah, rotation of 180 in either direction. About the origin. Was someone suggesting a double reflection? Yeah, double reflect. Oh, wow, yeah. Actually, I think Y equals X would have landed here. Or no, not quite. It would have been here. If I did Y equals X, because P would have been mapped here, N would have been mapped there. Yeah, that's tricky. But yeah, double reflect. Looks like X-axis, Y-axis, or vice versa. You guys agree? Disagree? No? Yeah. All right. Ooh. Oh, whoa, guys. I don't think these are congruent. The base here is 4. That base is 4. This diagonal, though, is not the same as that diagonal. It would have had to be like one of those. Or this one would have had to be here. Or over here. Right. Something like that. Those are not congruent. So I don't think so, friend. You're not going to fool me. Yeah. All right, here we go. Question 7 I selected. It says, determine whether the polygons with the given vertices are congruent. Use transformations to explain your reasoning. Let's see. I'll go with green for my pre-image. Over 2, up 4. There's some Q coming at you. R is 5, 4 over 1, 2, 3, 4, 5. Up 4, 1, 2, 3, 4. Oh, R right there. And S is over 4, 1, 2, 3, 4, and up 1. Looks like that. Something to that effect is my little triangle. Let's see what happens with this other fellow. Let's see, TUV. T is 6, 4. So 1, 2, 3, 4, 5, 6. Up 4. There's T. Wow, these guys are. Let's see. Let's see if I got space here. U is 9, 4. Hopefully I don't run out of space. Over 9, up 4. There you are. Oh. Let's see, and V is 8, 1. So let's see, 8, 1. Oh, did I put it on the 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, thank you with the save. I was assuming this was like, I didn't realize this was 11 across. So there you weren't. Let's see, there's and then V right here. Looks like something like that and that. So let's see, what's a transformation that maps one to the other, friends? If you do in fact think these are congruent.
X4, yeah. What? Oh! You know what? I thought R
and... Oh, yeah. And looks like Y stayed the same. So it could have been a transformation. Is there a way I could have done this with a reflection somewhere between the R and the T? It would that have worked? I'm first of all asking. Because yeah, this is down 3 over 2. This is down 3 over 2. That would not be the same, right? A reflection would have worked if it landed there. Then you could have imagined something like that. But yeah, it wouldn't have been a single reflection, to say the least. Right. Not a single reflection. Let's see. You spelled my last name wrong, but that's okay. Good. I don't blame you. It's W-single-U-O-T-I. Yeah, I did that. Oh, that looked like an O. But I guess maybe your handwriting's bad enough you can pretend. It's kind of like when you like don't know someone's name and you just like, hey, and you just like mumble it and you just, I don't know, you hope that it's close enough.
Hey, dude.
Hey, Chief.
How you spell their name?
Oh, that's a classic. Actually, yeah, one time when I was dating my wife, I was like, I didn't know how to spell her middle name, and then like her sister was like, do you even know her middle name? It's like, yes, and I did. So in her face, sister-in-law. Yeah, that's right. You heard me. Recorded on the internet. I'm gonna tag you in this somehow. Let's see, here's question 11. It says, triangle abaca is reflected in line K, and triangle A prime, B prime, C prime is reflected in line M. All right, a translation, let's see, is there a way, and those lines are parallel, by the way. A translation maps triangle ABC onto which triangle? Yes, my friend. All right, so you're saying, all right, what? B double prime? Oh, yeah, triangle. I was looking for like, I thought you were like naming the transformation there. But that's the one, right? It's mapping it this way, like so. And yeah, so that's triangle, thank you. A dub prime, B dub prime, C dub prime. Right. So yeah, so that's a transformation like such. And then it asks the question, which lines are perpendicular to AA double prime? So here's AA double prime right there. What do you suspect would be a perpendicular line? I almost went with parallel. Wow, that would have been embarrassing. It looks like, yeah, line K and, yeah, I gotta work on my lowercase k. K and M. Yeah, those look perpendicular right there. I agree. Yeah, it doesn't. Yeah, I wouldn't have enough evidence regarding any of the lines that make up the triangles. And then it says if the distance between K and M is 2.6. Let's see. I can't use that color, can I? So let's see. So if this distance is 2.6 from there to there, then the question is, what is the length of CC prime? What are your thoughts? 5.4? 2? All right. I think I agree because, yeah, it's going to be twice the distance since those lines of reflection were parallel. Perilous, even. All right, good. Let's see. It says, find the angle of rotation that would map A onto A prime. So let's see. Here's sorry. For A to A double prime. Oh my goodness, guys, this is a weird one. All right, what happened here? Okay, guys, wait a minute. So it got reflected from A to A prime. All right, over K. So the reflection happened over K first. You guys agree? Yeah. And then it got reflected over M. Wow, that's weird. So let's see, what do you think this angle would measure? Yeah. All right, okay. So it says, find the angle of rotation that would map this to that one. You're saying 30 degrees? I think you're right. And if we went back and looked at example 4, yeah, double reflections we realized could be the same as rotations if they were reflections that were over lines that would have intersected one another, which comes into play with this question here. It says, tell whether the statement is always, sometimes, or never true. Explain your reasoning. So 27, the composition of two reflections results in the same image as a rotation. Always true, sometimes true, never true. Well, the problem we just looked at when we had intersecting lines. Right. I don't know, I drew that completely wrong, didn't I? This is the same as a rotation. That was, yeah, one of our theorems that we did. So it's at least sometimes true. Is it always true? What's a counterexample to always being true? Let's see, the composition of two reflections results in the same image as a rotation. The book's counterexample is reflecting in the line y equals x, and then y equals x is not a rotation. That would map it back onto itself, which I would have kind of considered to be a 0-degree rotation. I don't think that's the best counterexample. I think the parallel lines case is a better example. Right. Parallel lines. I can't think of a rotation that maps this one to that one. But anyways, thanks for watching, internet friends. The answer was sometimes. Bye-bye.